October 23, 1929. 860 feet above Manhattan. British engineering consultants had declared American wooden scaffolding primitive stubbornness, completely unsuitable for modern skyscraper construction. Through the roar of wind and the clash of steel, construction superintendent John McGrath prepared to test 70,000 pounds of load on platforms built from nothing but old-growth Douglas fir timber. No modern steel tubes, no scientific calculations, no European approval, just 12 by 12 wooden beams that his father used building the Brooklyn Bridge, now supporting the secret spire assembly of what would become the world's tallest building. The Cambridge-educated experts insisted wood belonged in frontier cabins, not serious construction projects. Steel was scientific. Steel was predictable. Steel was safer. McGrath's crew stood nearly 900 feet in the air, trusting their lives to timber that European engineers claimed would split like matchsticks under such impossible loads. 8 decades later, modern aluminum scaffolding kills 60 workers annually from sudden collapse. McGrath's primitive wooden platforms, 0 deaths. How did trees cut when George Washington was president outperform today's advanced materials? Walter Chrysler stood in his temporary construction office on the 52nd floor, studying blueprints that would either make history or kill dozens of workers in the attempt. The morning sun cast long shadows across Manhattan, but Chrysler's attention focused entirely on the architectural drawings spread before him, specifically the cross-sectional view showing a 185-foot steel spire that would crown his building as the world's tallest structure. The challenge was unprecedented. 54,000 pounds of steel, 27 tons, had to be assembled inside the building's crown, then hoisted through the dome, opening by workers standing on scaffolding platforms 860 feet above the street. Add the weight of workers, tools, hoisting equipment, and safety margins, and the total load reached 70,000 pounds concentrated on wooden platforms that most engineers considered suitable only for painting houses. Construction Superintendent John McGrath entered the office carrying a leather portfolio thick with calculations. At 42 years old, McGrath commanded respect through competence rather than authority, his calloused hands and weathered face marking him as a man who had climbed every scaffold he asked his workers to trust. His father had been a carpenter on the Brooklyn Bridge, and McGrath carried those lessons in his bones. Wood was not just a material, but a living system that responded to load, weather, and time in ways that could be read by men who understood its nature. "The British consultants want another meeting," Chrysler announced without looking up from the blueprints. "They're still pushing their steel tube system." McGrath set down his portfolio and pulled out a chair. Sir Reginald Whitmore had arrived from Cambridge 3 weeks earlier, armed with slide rules and metallurgical expertise that impressed everyone except the men who would actually build the scaffolding. Whitmore's credentials were impeccable: structural engineering degree, consultancies on London's latest skyscrapers, published papers on load distribution theory. His solution was elegantly scientific: lightweight steel tubes with stamped connectors, precisely calculated to handle the required loads with minimal material and maximum efficiency. "Steel tubes look modern," McGrath said, opening his portfolio to reveal hand-drawn sketches of timber joints and load calculations written in his careful engineer's script. "But modern doesn't mean better when you're asking men to stake their lives on it." The mathematics seemed to support Whitmore's approach. Steel had predictable properties, tensile strength, compression limits, fatigue characteristics that could be calculated to 3 decimal places. Insurance companies favored steel because actuaries could quantify risk using established engineering tables. Wood, by contrast, was what Whitmore dismissively called variable biological material, no 2 pieces exactly alike. Properties that changed with moisture and age, strength that depended on grain orientation, and cutting techniques that couldn't be standardized. McGrath had spent the previous week studying the load requirements with the focused intensity of a man who knew that miscalculation meant widows and orphans. The secret spire would be assembled in 4 sections, each weighing 13,500 pounds. These weren't distributed loads spread evenly across large areas. They were concentrated impacts that would hit specific points on the scaffolding with the force of a locomotive. Conventional platforms would collapse instantly under such punishment, which was exactly what Whitmore predicted for wooden scaffolding. "The wood will split," Whitmore had declared during their last meeting, his Cambridge accent lending authority to the pronouncement. Elementary physics. Concentrated loads create stress fractures in timber that propagate until catastrophic failure occurs. Steel tube scaffolding distributes these loads across multiple connection points, preventing single-point failures. McGrath had listened politely, then asked a single question that revealed the gap between theoretical engineering and practical construction. "How many men have you seen die from scaffold collapse, Professor?" The answer was 0. Whitmore's expertise came from laboratories and calculation tables, not from standing on platforms 900 feet above the street while tons of steel swayed in Manhattan wind. McGrath had buried too many good men to trust theories over experience, and his experience told him that steel scaffolding failed without warning, one moment solid, the next moment gone, taking everyone on it into the void. "We'll use what my father used," McGrath told Chrysler, spreading out his sketches of traditional timber joints. Old-growth Douglas fir from Oregon, 12 by 12 beams, overbuilt by 400%. The specifications seemed almost primitive compared to Whitmore's precisely engineered steel system. Hand-selected timber cut from trees that had grown for 200 years, traditional joinery with wooden pegs that swelled when wet, creating connections that actually tightened under load. Hemp rope lashings that flexed with wind but never snapped under pressure, each platform built by the same carpenters who would work on it, ensuring that every joint was tested by men whose lives depended on its strength. Chrysler studied both proposals, torn between his immigrant respect for European expertise and his American entrepreneur's faith in practical innovation. The cost analysis favored steel, lighter materials, faster assembly, lower transportation expenses. The insurance calculations supported Whitmore's scientific approach over McGrath's craft traditions. Even the visual appeal worked against wood. Steel tubes looked modern and professional, while timber scaffolding appeared antiquated to observers who equated scientific appearance with safety. But McGrath's safety record spoke for itself. 23 years of construction supervision, 47 major projects, 0 scaffold-related fatalities. His methods might appear primitive to Cambridge-educated consultants, but 3,000 workers had carried home their paychecks because McGrath understood something that couldn't be calculated on slide rules, would talk to you before it failed, creaking and groaning warnings that gave men time to move to safety. Steel just snapped. The meeting that would decide the scaffolding system was scheduled for the following morning. Whitmore would present his steel tube calculations with European precision. McGrath would defend American craftsmanship with nothing but experience and intuition. Chrysler would choose between scientific theory and practical wisdom, knowing that either decision could determine whether his architectural ambition became a monument to human achievement or a tomb for dozens of working men. McGrath's victory in the morning meeting came not through eloquent argument, but through a single demonstration. While Whitmore presented his steel tube calculations with scientific precision, McGrath had quietly arranged for a section of his proposed wooden scaffolding to be erected in the building's construction yard. When Chrysler and the British consultant descended to street level, they found McGrath standing on a platform built from 4 12 by 12 Douglas fir beams, supporting a 10-ton load of steel girders that should have crushed any wooden structure into splinters. The timber held without a creak. Within days, flatbed trucks began arriving from Oregon bearing cargo that looked more suited to frontier homesteading than modern skyscraper construction. Each beam represented 2 centuries of Pacific Northwest growth, old-growth Douglas fir cut from trees that had been saplings when Lewis and Clark crossed the continent. The wood arrived in rough-hewn sections, bark still clinging to edges, sap stains marking where the tree had fought insects, and weather through decades of mountain winters. McGrath's selection process resembled a master craftsman choosing instruments more than a construction superintendent ordering materials. Each beam weighed exactly 400 pounds and measured a precise 12 inches square, but no 2 pieces were identical. The grain patterns told stories that only experienced carpenters could read. Tight rings indicating slow growth and maximum strength, wide rings marking years of abundant rainfall that created weaker sections, knots that either strengthened or weakened depending on their size and position within the timber's structure. Seamus O'Brien, McGrath's lead carpenter, had learned to read wood grain in the hills of County Cork before emigrating to America with nothing but his tools and his father's knowledge of traditional joinery. His hands moved across each beam like a physician examining a patient, feeling for the subtle variations in density that indicated a timber's load-bearing capacity. Wood with 35 pounds per cubic foot density was ideal, strong enough to handle massive loads, flexible enough to bend rather than snap under sudden stress. The grain was so tight that O'Brien could count 40 growth rings within a single inch, each ring representing a year of patient growth that created strength no factory could manufacture. The construction specifications defied every principle of modern engineering efficiency. No metal fasteners connected the beams. Instead, O'Brien's crew used wooden pegs cut from the same Oregon timber, shaped by hand to fit precisely into holes drilled with auger bits that had been forged by blacksmiths rather than manufactured by machine companies. When moisture from Manhattan's humid air reached these wooden connections, the pegs swelled, creating joints that actually tightened under load rather than loosening over time. Hemp rope provided the crucial lashing connections that held entire platform sections together. Unlike wire rope that could snap without warning, hemp fibers stretched and flexed with building movement, absorbing wind loads and thermal expansion that would have shattered rigid connections. Each rope was tested by the men who would stake their lives on it. O'Brien personally inspected every knot, every splice, every connection point that would support human weight nearly 900 feet above Manhattan's streets. The revolutionary aspect of McGrath's system wasn't the materials, but the method. Each scaffold platform was built by the same carpenters who would work on it, ensuring that every joint was tested by men whose survival depended on its strength. No contractor bidding system, no separation between builder and user, no theoretical calculations that divorced engineering from reality. When O'Brien's crew lashed together a platform section, they immediately loaded it with twice the expected working weight and stood on it while other workers jumped up and down to test its flexibility and strength. By the 50th floor, McGrath's wooden scaffolding was outperforming every prediction that Whitmore's calculations had generated. Load tests revealed safety factors of 6 to 1, double the strength that the British engineers' steel tube system could provide. Construction speed reached 4 floors per week, faster than any previous New York skyscraper project. Most remarkably, the injury reports showed 0 scaffold-related accidents, despite the massive loads and dangerous heights that the wooden platforms handled daily. The breakthrough came when O'Brien developed what his crew called the flex joint, a lashed connection that allowed wooden platforms to move with wind loads while distributing weight across multiple support beams. Traditional rigid connections would have transferred stress to single points, creating failure zones that could collapse entire sections. O'Brien's innovation used the natural flexibility of wood and hemp to create a system that breathed with the building's movement, absorbing forces that would have destroyed less adaptable materials. Tony Santangelo, foreman of the Italian rivet gangs, had initially viewed wooden scaffolding with the skepticism of a craftsman trained in European metalworking traditions. His crews had worked on steel structures from Naples to New York, trusting their lives to manufactured materials with predictable properties and scientific specifications. But after 3 weeks working from McGrath's wooden platforms, Santangelo made a request that surprised everyone. He wanted his rivet gangs moved from the building's steel staging to the wooden scaffolding sections. "Wood talks to you," Santangelo explained to McGrath during a lunch break on the 60th floor. "It creaks and groans and tells you when it's getting tired. You can feel it flex under your feet, but it never just disappears. Steel scaffolding feels solid right up until it snaps. No warning, no second chances." The Italian crews discovered that wooden platforms actually improved their work quality. The slight flexibility absorbed the vibration from pneumatic hammers and rivet guns, reducing fatigue and improving precision. When wind loads hit the building, steel staging transmitted every gust directly to the workers, forcing them to stop work and seek shelter. The wooden platform swayed gently with the building's movement, allowing the rivet gangs to continue working in conditions that would have shut down conventional scaffolding operations. Word of the wooden scaffolding's performance spread through Manhattan's construction community with the speed of industrial gossip. Contractors who had initially mocked McGrath's frontier methods began requesting meetings to study his joinery techniques. Insurance investigators who had predicted catastrophic failures found themselves documenting the safest construction project in New York City's history. Even Whitmore, the Cambridge-trained engineer who had dismissed American timber as primitive stubbornness, was forced to acknowledge that McGrath's system exceeded every performance metric that scientific calculation had established. 40 blocks south of McGrath's wooden scaffolding triumph, architect H. Craig Severance stood in his own construction office overlooking the East River, surrounded by engineering consultants who promised that European scaffolding technology would deliver the Manhattan Company building, soon to be renamed 40 Wall Street, faster and more efficiently than any American timber system could achieve. Severance had watched with growing concern as reports of the Chrysler Building's progress filtered through Manhattan's tight construction community. Each story of McGrath's wooden platforms carrying loads that should have been impossible, making Severance question whether his own sophisticated approach was sophisticated enough. The scaffolding system rising alongside Severance's building represented the pinnacle of European engineering innovation. Lightweight steel tubes manufactured in Birmingham connected through stamped steel joints that had been precision engineered to handle calculated loads with mathematical certainty. Aluminum decking provided working surfaces that weighed 60% less than wooden planks while offering superior weather resistance and professional appearance that impressed visiting investors and city inspectors. The entire system could be assembled with standardized tools by workers who needed minimal training, unlike McGrath's craftsmen who required years of experience to properly lash timber joints. Dr. Heinrich Wolff, the German engineering consultant who had designed the scaffolding system, presented impressive performance statistics that made Severance's European approach appear definitively superior to American timber methods. The steel tubes weighed 30% less than equivalent wooden beams, reducing transportation costs and assembly time while eliminating the unpredictable variations in strength that plagued natural materials. Weather resistance was absolute. Steel didn't rot, warp, or weaken with moisture like wood. Most importantly, every component had been tested in laboratories and certified to precise load specifications that could be verified by any competent engineer. Assembly speed exceeded every projection. Where McGrath's carpenters spent hours selecting, fitting, and lashing individual timber joints, Severance's crews connected standardized steel components in minutes using pneumatic tools and stamped connectors that clicked together like mechanical puzzles. By early October 1929, both Manhattan skyscrapers raced toward completion, with Severance's building showing a slight lead in both height and construction speed. The engineering press celebrated the 40 Wall Street project as vindication of scientific construction methods over traditional American craft techniques. The first warning signs appeared so subtly that even experienced foremen missed their significance. Small stress cracks developed in stamped steel connectors after repeated loading cycles, hairline fractures that were invisible unless workers knew exactly where to look and had adequate lighting to spot them. The aluminum decking, while impressively lightweight, began developing small dents and deformations under the impact of dropped tools and materials, creating tripping hazards that grew worse as construction progressed. Workers reported that the steel scaffolding felt different from traditional platforms, though none could articulate exactly what had changed. The first actual failure occurred on October 15th during routine material handling on the 62nd floor. A stamped connector cracked completely under load, dropping a section of aluminum decking 6 inches before adjacent connections caught the weight. No workers were injured, and the failure was attributed to a defective part rather than systemic design problems. Dr. Wolff's investigation concluded that the connector had been improperly manufactured, falling below the tolerances specified in German industrial standards. Replacement parts were ordered, and construction continued without interruption. The second collapse happened 3 days later under nearly identical circumstances. This time, the failure propagated through multiple connections as cracked stamped joints transferred loads to adjacent components that weren't designed to handle the additional stress. A 12-foot section of aluminum decking tilted 45 degrees before emergency bracing prevented complete collapse, but 5 workers scrambled for safety as their platform shifted beneath their feet. The incident report blamed unexpected load combinations that exceeded design specifications, though the actual weights involved were well within the system's rated capacity. By October 20th, Severance's construction crews were reporting something that McGrath's carpenters had never experienced: fear of their own scaffolding. "Steel scaffolding feels solid until it isn't," explained foreman Giuseppe Torino, whose crew had been working the 65th floor when the second collapse occurred. "You can't hear it getting tired. Wood creaks and groans and gives you warning. This stuff just goes from fine to gone in 1 second." The critical test came on October 23rd, when autumn winds reached sustained speeds of 45 miles per hour across Manhattan's canyon corridors. McGrath's wooden scaffolding on the Chrysler Building flexed and swayed with the building's movement, absorbing wind loads through the natural flexibility of timber and hemp lashings that had been designed to work with forces rather than resist them absolutely. Workers continued their tasks throughout the storm, trusting platforms that moved but never failed, that creaked warnings but never collapsed without notice. Severance's steel scaffolding responded to the same wind loads with the rigid resistance that European engineering principles demanded. Steel tubes and stamped connectors transferred every gust directly through the system, creating stress concentrations at connection points that had been calculated for static loads rather than dynamic wind forces. The third failure occurred at 11:37 that morning, when sustained 45-mile-per-hour winds combined with normal working loads to exceed the stress limits of connectors that were already weakened by repeated loading cycles. This time, an entire platform section collapsed completely. 8 workers dove for safety as their aluminum decking tilted beyond recovery, crashing 40 feet to the next scaffold level in a cascade of bent steel and twisted metal. Miraculous lie. No one died, though 3 men required hospitalization for injuries that would have been impossible on McGrath's flexible wooden platforms. The professional appearance and scientific precision of European scaffolding technology had produced exactly the catastrophic failure that McGrath's primitive timber methods had been designed to prevent. Work stopped immediately at 40 Wall Street while engineers investigated the failure. Severance walked through the damaged scaffolding sections with Dr. Wolf, studying bent steel components that showed no warning signs before collapse. The German consultant's instruments could measure stress fractures to precise tolerances, but they couldn't predict when stamped connections would fail or provide the early warning systems that wooden platforms offered through natural flexibility and audible stress indicators. 40 blocks north, McGrath's crews continued working through the same storm conditions that had shut down the supposedly superior European system. The wooden scaffolding that Cambridge-educated engineers had dismissed as frontier stubbornness was proving more reliable than laboratory-tested steel components, more adaptable than precision-engineered connections, safer than scientifically calculated systems that looked modern but broke without warning. The morning of October 23, 1929, arrived with the crisp clarity that only autumn in Manhattan could deliver. 860 feet above the bustling streets, McGrath stood on his wooden scaffolding platform, reviewing the final preparations for an operation that would either crown his career or end it in catastrophe. The secret spire sections waited in the building's upper floors like sleeping giants, 4 pieces of architectural artistry that would transform Chrysler's building from merely tall to definitively the world's tallest structure. Each spire section represented 13,500 pounds of precision-engineered steel, crafted in secrecy to prevent rival architects from learning the true height of Chrysler's ambition. The combined weight of all 4 sections, plus workers, hoisting equipment, and safety margins, would subject McGrath's wooden platforms to 70,000 pounds of concentrated load, a test that no timber scaffolding in construction history had ever attempted to survive. McGrath had spent the previous week calculating and recalculating the load distribution across his Douglas fir platform system. 200 square feet of old-growth timber would bear the entire weight, creating a load of exactly 350 pounds per square inch. His father's voice echoed in his memory from those Brooklyn Bridge days 3 decades earlier. Wood loaded to 50% of its breaking strength will carry that load for 50 years. Douglas fir could handle 700 pounds per square inch before failure, which meant McGrath's calculated load fell precisely within the safety margin that generations of American carpenters had trusted with their lives. Seamus O'Brien supervised the final inspection of every timber joint and hemp lashing that would support the operation. His experienced hands tested each wooden peg, each rope connection, each point where tons of steel would transfer their weight through the scaffolding system to the building's steel frame. The flex joints that he had innovated during the building's construction would face their ultimate test. Either they would distribute the massive loads as designed, or they would fail spectacularly in front of half of Manhattan's construction community, which had gathered to witness this unprecedented feat of American engineering. Walter Chrysler himself had climbed to the scaffolding level to observe the operation, his presence adding weight to an already pressure-filled situation. Alongside him stood representatives from 3 major newspapers, 2 competing architectural firms, and Sir Reginald Whitmore, whose European expertise McGrath had systematically disproven over the past 6 months. The British engineer maintained professional courtesy, but his presence carried an unspoken message. He was waiting to document the catastrophic failure that his calculations still predicted for American timber methods. The hoisting operation began at 7:32 in the morning with the precision of a military campaign. Tony Santangelo's rivet crews positioned themselves at strategic points along the scaffolding, ready to guide each spire section through the complex maneuvers required to position it correctly within the building's crown assembly. The crane operators, perched in their steel cabs high above the city, communicated through hand signals and whistle codes that had been rehearsed dozens of times during the previous weeks. The first spire section rose smoothly through the dome opening, 13,500 pounds of steel moving with the grace of a dancer under the expert guidance of crane operators who had lifted everything from bridge girders to locomotive boilers during their careers. McGrath's wooden platform absorbed the load without visible deflection, the Douglas fir timbers distributing weight through their network of traditional joints, exactly as his calculations had predicted. The hemp lashings stretched slightly under load but held firm, their natural flexibility allowing the platform system to accommodate the dynamic forces created by wind and crane movement. Success built upon success as the second and third spire sections joined their predecessor in the building's crown. Each lift demonstrated the superiority of McGrath's wooden scaffolding over the rigid steel systems that European engineering favored. Where stamped steel connections would have transferred shock loads directly through the structure, creating potential failure points. The traditional timber joints absorbed and distributed forces through the natural flexibility that only organic materials could provide. By noon, 3/4 of the secret spire waited in position, ready for final assembly that would make Chrysler's building the undisputed champion of Manhattan's skyline race. The fourth and final spire section began its ascent at 12:45, rising through Manhattan's autumn air with the weight of architectural history riding on its steel framework. McGrath watched from his wooden platform as the massive piece cleared the building's lower levels, approaching the critical moment when it would transfer its full weight to timber scaffolding that had never been tested under such extreme conditions. The city seemed to hold its breath as the final component of America's tallest building approached its destination. At exactly 12:57, the primary crane cable snapped. The failure occurred without warning, exactly as McGrath had always feared with mechanical systems that provided no advance indication of impending breakdown. One moment, the 13,500-pound spire section hung securely from steel cables. The next moment, it swung wildly through the air, transformed from controlled cargo into a massive pendulum that threatened to demolish everything within its arc of destruction. Workers scattered across the scaffolding as the loose spire section swept toward McGrath's wooden platform with the accumulated momentum of its fall and swing. The impact force would exceed 40,000 pounds. Nearly double the load that any scaffolding system had been designed to handle, delivered not as gradual weight increase, but as sudden shock that would test every joint, every beam, every connection point that O'Brien's crew had crafted during 6 months of careful construction. The steel section slammed into the Douglas fir platform with the sound of a locomotive collision, transmitting forces that would have instantly destroyed any rigid scaffolding system. Workers threw themselves flat against the timber decking as the entire platform shuddered under impact loads that exceeded every engineering calculation. The city below watched in horrified fascination as McGrath's primitive wooden scaffolding faced the ultimate test that would either vindicate American craftsmanship or confirm European predictions of catastrophic failure. In that frozen moment, with 40,000 pounds of impact force challenging 6 months of traditional timber construction, the reputation of American building methods hung in the balance alongside the lives of every man standing on McGrath's wooden platforms 860 feet above Manhattan's unforgiving streets. The impact reverberated through McGrath's wooden scaffolding like thunder rolling across Manhattan's concrete canyons. 3 12 by 12 Douglas fir beams split under the 40,000-pound blow, their grain separating along lines that had been invisible until tremendous force revealed the natural fracture patterns hidden within 2 centuries of Pacific Northwest growth. In a steel scaffolding system, such damage would have triggered immediate catastrophic collapse, sending platforms and workers plunging 860 feet to the street below. But McGrath's timber network did something that European engineering had never anticipated. It redistributed the massive load through its web of lashed joints and wooden pegs, transforming what should have been fatal structural failure into manageable localized damage. Seamus O'Brien was the first to move, his carpenter's instincts reading the platform's condition, even as dust and debris still settled from the impact. The flex joints that he had developed over months of construction proved their worth in seconds of crisis, allowing undamaged sections to absorb loads from the broken beams without creating new failure points. Hemp lashings stretched but held, their organic fibers distributing stress across multiple connection points instead of concentrating forces at rigid attachment locations. The wooden platform sagged visibly where the spire section had struck, but it remained intact, supporting every worker who had trusted their lives to American timber craftsmanship. McGrath knelt beside the damaged beams, running his hands along the split grain with the focused intensity of a physician examining a patient. The fractures were clean breaks that followed the wood's natural structure rather than the chaotic shattering that would have accompanied steel failure. Most importantly, the splits had occurred in predictable locations where the timber's grain provided advance warning through visible stress patterns. Any experienced carpenter could have read these signs and anticipated exactly where failure would occur, unlike the sudden catastrophic collapse that characterized modern engineered materials. 90 minutes, McGrath announced to O'Brien, his voice carrying across the platform with the calm authority of a man who had prepared for exactly this contingency. We replaced these 3 beams without moving a single man off this scaffold. What followed was a masterpiece of American craftsmanship, executed under the most demanding conditions imaginable. O'Brien's crew had spent 6 months learning to work as an integrated team, each carpenter understanding not just his own specialty, but how his work connected to every other man's contribution. They moved with the coordinated precision of a championship baseball team, each worker anticipating the next step while maintaining constant awareness of their position 860 feet above Manhattan's streets. The replacement beams had been pre-positioned on lower scaffold levels as part of McGrath's comprehensive safety planning. No complex crane operations were required, just the systematic application of block and tackle systems that American carpenters had perfected during 2 centuries of barn raising and bridge building. Each 400-pound timber was guided into position through human coordination rather than mechanical precision, lifted by men who understood exactly how Douglas fir behaved under load and how traditional joinery would distribute forces through the completed structure. The damaged beams came out in sections, carefully removed to prevent any sudden load shifts that might compromise the platform's stability. O'Brien personally inspected each replacement timber, his experienced hands reading grain patterns that told him exactly where to position the beam for maximum strength. The wooden pegs that secured each joint were shaped individually, fitted by craftsmen who understood that no two pieces of wood were identical and that successful construction required adapting standardized techniques to the unique characteristics of each natural material. Exactly 87 minutes after the crane cable failure, the final wooden peg was driven home and McGrath's scaffolding was restored to full strength. No worker had been removed from the platform during the repairs. No complex engineering calculations had been required. No factory-manufactured replacement parts had been ordered and delivered, just American craftsmanship and Douglas fir timber working together to accomplish what European scientific methods had declared impossible. The spire installation resumed immediately. The damaged steel section was secured and repositioned, then joined by its three companions in a precise choreography that transformed architectural drawings into three-dimensional reality. Each 13,500-pound component settled into place with the satisfaction of a puzzle piece finding its proper home. By 4:30 that afternoon, all four sections were positioned correctly, ready for the final assembly that would crown Chrysler's building as the world's tallest structure. The official completion ceremony took place on November 13, 1929, with Walter Chrysler himself standing on McGrath's wooden scaffolding to witness the installation of the final decorative elements that brought the building to its full height of 1,046 feet. 77 floors completed in 20 months of construction. 0 scaffold-related fatalities among the 3,000 workers who had trusted their lives to timber platforms that European consultants had dismissed as primitive and dangerous. Sir Reginald Whitmore attended the completion ceremony, his professional courtesy intact despite the systematic refutation of every prediction his Cambridge training had generated. The British engineer's farewell conversation with McGrath carried undertones of respectful bewilderment. Theoretical engineering had been outperformed by practical craftsmanship, scientific calculation defeated by traditional knowledge passed from father to son across generations of American builders. The final accounting revealed the true magnitude of McGrath's achievement. 3,000 workers had carried home their paychecks, their families spared the widowhood and orphanhood that claimed dozens of lives on every major construction project. The scaffolding system that protected them had been built entirely from trees that began growing when George Washington was president. Old-growth Douglas fir that represented America's natural resources married to immigrant craftsmanship, both tested by time and proven reliable when lives hung in the balance. Decades later, when aluminum scaffolding began claiming 60 lives annually through sudden collapse, construction historians would study McGrath's methods and rediscover the fundamental principle that modern builders had forgotten: materials chosen for cost and convenience rather than performance under pressure. Calculations prioritized over craftsmanship, theory valued above experience. The result was scaffolding that looked modern and scientific but failed without warning, killing workers at rates 30 times higher than McGrath's primitive wooden platforms had ever produced. American ingenuity had solved the problem once, using nothing but trees and traditional knowledge. The solution waited in construction archives, ready to save lives again whenever builders remembered that the newest technology wasn't always the safest choice.